Let x be a random variable that follows a gamma distribution with the parameter alpha and lambda. Where alpha and lambda is greater than 0, calculate the expected value of x and the variance of x. Let's first compute the expected value of x. The expected value of x is equal to the integral 0 to infinity x times the density function of gamma distribution, d of x, and this is equal to 0 to infinity x. The density function of a gamma distribution is given by lambda to the alpha divided by gamma alpha x alpha minus 1 e to the negative lambda x d of x, and this is equal to lambda to the alpha divided by gamma alpha. So 0 to infinity x to the alpha times e to the negative lambda x d of x. Now we're going to write this as alpha plus 1 minus 1. So the reason is that this is going to we're going to use the property of a gamma distribution here, a gamma function here. So here's the property of a gamma function. We have this formula. So this is equal to gamma alpha divided by lambda to the power of alpha. And you can see the inside this integral is exactly the same as this one, except that the alpha here is replaced by alpha plus 1, right? So we're going to apply this formula, replacing the alpha with the alpha plus 1. So this is equal to lambda to the power of alpha divided by gamma alpha, gamma alpha plus 1 divided by lambda to the alpha plus 1. So we can then apply this second property of a gamma function. Gamma alpha plus 1 is equal to alpha times gamma alpha. So we're going to apply this property. So this is equal to lambda to the alpha gamma alpha times alpha times gamma alpha divided by lambda to the alpha plus 1. And this is going to cancel out. And this is equal to, and we're going to cancel some of these two. So this cancel out. And it's only lambda is left. So this is equal to alpha divided by lambda. Now next we want to compute the variance of x. Let's first compute the expected value of x squared, and this is equal to the integral from 0 to infinity x squared, again the density function of lambda distribution, which is lambda to the alpha divided by gamma alpha x alpha minus 1 times e to the negative lambda x d of x, and this is equal to lambda alpha to the power of alpha divided by gamma alpha. Here we just take this item out, right? So the integral from 0 to infinity x to the power of alpha plus 2 minus 1 times e to the negative lambda x d of x. Now again, we're gonna calculate this piece using the first property we showed here. So now alpha here would be alpha plus 2, right? So it's alpha plus 2 here. So we're going to apply the formula here. So this is equal to lambda to the alpha divided by gamma alpha, gamma alpha plus 2 divided by lambda to the alpha plus 2. So we're going to use the property here as well. So lambda to the alpha divided by gamma alpha times the numerator now becomes, we're going to apply this formula here. So this is going to be equal to alpha plus 1 times gamma alpha plus 1. So here we're going to apply this formula, but alpha here would be alpha plus 1, right? So we're going to apply this formula here. So divided by lambda to the alpha plus 2, and we're going to apply the formula. We're going to apply this formula to this piece again using the formula here. So this is going to be equal to lambda to the alpha divided by gamma alpha times alpha plus 1 times alpha gamma alpha divided by lambda to the alpha plus 2. So this is the entire thing. After some cancellations, this is going to be equal to alpha times alpha plus 1 divided by lambda squared. Now we have the expected value of x here. We have the expected value of x squared here. So now let's compute the variance. The variance of x is equal to the expected value of x squared subtract the expected value of x squared. So this is equal to alpha times alpha plus 1 divided by lambda squared subtract alpha divided by lambda squared. And this is equal to alpha divided by lambda squared. Thank you for watching.